Okay, I'm Jim Holland, and this is Design at Large. It's a great pleasure to introduce Tom Defanti, who's our speaker today. He's really one of the incredible pioneers of scientific visualization. And like many Design at Large speakers, I can't tell you his whole list of awards and things. He's a fellow of ACM. And he's had like a tremendous impact on, I think, SIGGRAPH and that whole organization right from the start. He chaired SIGGRAPH for a number of years. He was, I think, influential in starting the electronic theater, which is sort of my favorite part of SIGGRAPH kind of meetings. And he also started SIGGRAPH video reviews, which I think was very influential in getting out to a large population some of the things going on. He did his PhD at Ohio State University. He created the GRASP programming language for doing three-dimensional real-time animation. I asked Larry to give me some things to embarrass him with. But he knows too much about Larry, so Larry didn't tell me anything. But he did mention, he reminded me that GRASP had been used to do the only 3D computer graphics in the original Star Wars system, which is sort of very interesting. Personally, I came across Tom's work maybe before many of you were born, but in 1987, he led a panel he co-chaired a panel on visualization and scientific computing. That was back in the days, I think Gordon Bell was associate director of SENSEI. That was the days when NSF had just funded 5 supercomputing centers around the country. ARPA, I think, had just become NSFNet in those days as it was transitioning. And the panel had just an amazing set of folks, in addition to Tom. Alvy Ray Smith, who's talked in the series, founder of Pixar, Jim Blinn, Jim Clark, Turner Whitehead, Fred Brooks. And the report, which I was very much influenced by, described visualization as emerging as a sort of a major new field and of applying computers in science. And it was offering a way to see the unseen. And I think a lot of what people have worked in visualization have worked on is to try to make the invisible visible kind of things. And that report really heralded this. They recommended a new initiative to get visualization tools in, quote, the hands and minds of scientists. And I think that that's had tremendous impact. And I don't think there's few people who've done as much to accomplish that, of getting these kind of tools into the hands and minds of scientists as Tom. And today he's going to tell us some of his recent steps in that direction. After the talk, he's going to invite you over to see some of this actually running, the wave stuff, and we'll all troop over there to see it. He's going to talk about big VR for big data and the next wave. And as a surfer, I love using the acronym of WAVE, of sort of wide-angle virtual environments. So he's going to tell us about the present.
So thank you for that setup. You really did things. Now, truth be told, the visualization report, which got everybody to change their business card to have the word visualization in it, there were 2 things. First of all, Alvy was the first one to start using that term with respect to computer graphics. We had the electronic visualization lab a decade and a half before in Chicago. It's a good word. And it melded then computer graphics and image processing or pattern recognition, which are 2 very different fields, and they still are, but they needed to talk to each other. So that was, and this, typical of Larry, he had this idea, and then he said, Tom, you do it. So I'm still here, and I'm still doing Tom, you do it stuff, and I was doing it right up until 4 o'clock today, and so on. So I'm going to, this of course is the star cave up here, and people who have contributed to these things, among many others. going to really talk to you about big VR today, since everybody's talking big data and big everything, you know. But, you know, everybody, however, is focusing on little VR, you know, the kind you stick on your head. So I'm going to talk about big VR. But before we go there, I'm going to start with a couple of videos. And the first one is a video that was made in 1977, actually, about the Star Wars work that we did in 1976. Now, this was extremely laborious. It took us months to do this 45-second thing that was very primitive. It was kind of intentionally primitive. George Lucas wanted it to look primitive. Better computer graphics were available then, but they looked kind of like his models, and he wasn't interested in that. He wants something that looks like a computer did it, right? A long time ago, far, far away. So this thing, I could go a whole hour on this particular thing. You know, all I want to say a couple of things is that this is 40 years ago. And I was 27 years old at the time. Now, how many of you in this audience are 27 years old or younger? Come on, raise your hands. Okay, so just think about what you're going to be doing in 40 years. Okay? Now, this is what Jim was talking about. When I first ran into Larry, he had put this NSF-net thing together with NSF and a bunch of other people, and here this thing was running at 56 kilobits a second. Now that was essentially what a digital phone line, analog phone line can do. And, but that was 200 times faster than the 300 BPS modems we were using to connect to our computers, or any of you who actually remember that kind of acoustic coupling stuff. So that was a big deal, although when I first met Larry, I was in the audience and I raised my hand and I said, well, I don't understand how you're going to change science with something that communicates at 1/10 the speed of my Apple II floppy to the Apple II, you know. And Larry said, I'm going to talk to you. And I started working for him. So that was that story. And that was 1987, I guess, 1986. So what's happened in between? We developed an incredible amount of networking technology, and I've been in the middle of that for a variety of reasons that mostly have to do with the fact that people who fund this stuff want to see things, and networking people really don't know how to do that, and so they want it's the National Science Foundation, not the National Networking Foundation. So they wanted somebody to show applications. And, but then it kind of stalled. We did this major build out in the 90s, the late 90s, and then it kind of stalled for a little while. And mid last decade, Arden Bement, who was the director of the NSF, said basically that we've got too much data. We've got these great national networks, but when they hit the campuses, they essentially go onto dirt roads. And that really had to improve the campus infrastructure. Now, it took years before these things, as typical, got into practice, and NSF funded a second generation of network upgrades, which our campus has actually been at the forefront of and gotten 2 of those awards. Meanwhile, the Department of Energy decided to do a thing they called the Science Demilitarized Zone, which is a way of optimizing science data transfers to get around the fact that most of our networking comes through piles of equipment to keep out the bad guys. But if you cleverly pre-filter the bad guys, in other words, you trust who you're getting stuff from, you can get rid of all that stuff. And so this is part of what we're doing next. And I'm going into this very quickly. So NSF then funded over 100 campuses to build these DMZs based on the ESNet concept. And the one that we built here, that Phil Papadopoulos is the PI of, is called Prism. It goes all over campus. It runs mainly at 40 gigabits per second, which is very fast. And it's allowed us to put together things as complicated as this, where people connect to supercomputers, several supercomputers, all for the same project, our big viz screens, huge data stores, and so on, and out to the labs themselves. In order to do this, Phil Papadopoulos designed a thing that I named FIONA, for Flash I/O Network Appliance, that uses flash memory, solid-state disks, to keep up with the networking. The problem with networking is if you come crashing into the campus or anything and can't keep up with it, the networking protocols, TCP, tell the thing to back off. And it takes a while for it to get back up to speed, and then it backs off again. And so if you ever looked at networking charts that look like this, which of course doesn't work. And so you have to make it so the thing that's receiving it can take it as fast as it's coming to it. And that was the whole tuning of this. We've actually known how to do this for many years, but the scientists wouldn't use the protocols that we came up with, so we decided to program around it. A year ago, we did this thing to prove that it could work, and got up to 36 gig out of 40 to various places, and 9.6 out of 10. CNEC developed these dashboards to show all the interconnections of these campuses. Now, here's an example of trying to do something between here and the University of Amsterdam, where they had what they call a policer, which was something that was looking closely at the packets coming in, and it was running really, really slow. And this policer had been there for years and years, and nobody even remembered it, but it was in the way. And with months of work of, as Phil Populus calls it, skinning your knuckles, one day they unplugged that thing, and look what happened. It went from nothing to, almost 7 gigabits a second, and this is over, 10,000 kilometers, right? So, so we built this thing called the Pacific Research Platform, and NSF funded it to hook together 20 universities, mostly on the West Coast, and as a regional experiment of how to kick this into the next gear. And now we have these things are called MAD dashes, and I don't even know what MAD stands for, and dash is obviously dashboard. And you can mouse over this thing and see what anybody's doing between the transfers that we run several times a day as tests, and see what's going on. So we're now bringing this back up after we started this project and got the funding. We're bringing it back up between the campuses, and we've pushed this all over to layer 3 now. It was layer 2, and if you don't know what that means, it doesn't matter. Okay, so, but where's all this big data coming from? So there is a project called Jupyter Hub at Berkeley and our pattern recognition non-von Neumann computing lab here that's just started. There's biomedical, earth sciences, particle physics, astronomy and astrophysics, and scalable visualization. So again, I'm running through these fast because I lost some time. So we've been building these boxes. These FIONA boxes are quite expandable, and here's one that's got 28 cores of CPUs, some flash, and a lot of NVIDIA's got 15,000 NVIDIA cores and dual 40 gigabit NICs. So, and this is just a box, right? It just fits there. It's this big, 3U. And it's a supercomputer, right? I mean, it's from a supercomputer a few years ago. And it's about 20 grand, which, for any of you who actually pay bills, that's what one grad student costs for 1 quarter. So it's not a lot of money. We've also just started with this pattern recognition lab. So Jim, I'm giving you a whole bunch of lectures to each one of these is a beautiful lecture. This is a chip. This thing it fits in is the size of my phone here, but maybe twice as thick. And it has 256 million synapses and 1 million neurons. This is IBM's True North chip. Javier Gerardo here is just come to us back from Qualcomm after he did his PhD dissertation with me in this area years ago and went off to Qualcomm. And now we've hired him back to work on this project, and we're really happy about that. Okay, now I'm going to move to VR. So I picked up this cartoon from 1951, which are the early days of home television. And look what it says. One nice thing about television, you don't have to pick out where to look. So what are they referring to here? They're referring to the fact that a sports game or theater or whatever, you look all over the place and you actually have to figure out where to look. But on TV, they tell you. Well, we blew that up with VR because now you don't know where to look anymore, right? We ruined TV. So this was the first cave we built, and Larry had a lot to do with this too. The first one was in Chicago. The second one was in Urbana at NCSA where Larry was. The third one was at Argonne. The fourth one was at DARPA. But it was expensive. This is what you're going to see later. This is the wave It's got, we built this a couple of years ago. It's 35 megapixels per eye instead of 1 megapixel per eye. And instead of $1 a pixel, it's it's a penny a pixel. Okay, so that's good. You know, orders of magnitude are always good. This room also has a terabit network in it, which of course was inconceivable not too long ago, but here we go. And this is this was the original vision I had for these caves, was that I happened to be getting a suit for when I used to ask for a lot of money, and I was standing in a tailor's mirror and said to myself, well, gee, this kind of works. If I move over here or over here, I can see that there's no occlusion, that the image moves with me. And you know, one of the things we learned from doing ray tracing was that, you know, light goes both ways, you know. I mean, in the real world, it only goes one way, but in computation, it's sometimes a good deal to make it go the other way. Simplifies it. So I said, why don't we build something that replaces the screens in a tailor's mirror with, you know, screens. Now, it turned out we could only do it with projectors back then, but now we can do it with big home TVs. So here's the thing we built a year ago or so, and 2 years ago. And this thing is now down to half a centipixel. And it works really well. So those of you, we've got this one over in the Shiley Eye Center now to help figure out has some wayfinding experiments for people who have onset Parkinson's as a test. So how do we take these pictures? We've seen a bunch of different images, and the rest of this thing, which I'm going to race through now, is about how do we get these realistic images. These images exceed your visual acuity, which is something that you don't get out of head-mounted displays, and you won't for some time. Well, head-mounted displays are kind of fuzzy looking, like the cave was in 1992. But there are techniques that we perfected to take at least still images in stereo. And again, you'll see some over in the wave. I'm going to show you how we take these. Now, LiDAR and structure from motion, which is what was used in the baptistry, the Florence imagery that I showed you as a second video, is a different lecture. Another lecture for you to propose, Jim. So a friend of mine named Dick Ainsworth, who I've been working with since 1973, developed this camera system with Dan Sandin. And it is basically 2 snapshot Lumix cameras that are on a gigapan robot. And we generate, we take this thing out in the field. So here's Tom Levy with David and Aaliyah off in a beautiful place in Greece. And here I am in Egypt 5 years ago, I don't know, 5 years ago, during the revolution there, taking pictures. So what happens, you get 72 images for each eye, so 144 together like this. You stitch them together, and the image looks like that. But when you wrap it back around a sphere, basically, it looks like that. And I'm going to show you in a second, since I can't do this. I used to be able to do this inside of these things. I'm going to pop out and just show you one of these things in real life here. And let me move it over. Can I make it big enough? And then this is, goes around like that. I'm going to do it slowly so I don't make you dizzy. But this image is so good that there was the current governor of Wisconsin successfully limited the power of unions to negotiate for salary increases, and the workers stayed. They sit in this building, and part of the response of the government in Wisconsin was to claim that the protesters had damaged the building. Now, it just so happened we had this ultra-resolution thing, and we pointed out that the cracks are already there and that there was no damage. So anyway, I felt particularly proud about that. I went through college on a union scholarship, so I really am a union sympathizer. Okay, so how do we, let's try and comes back without crashing. Good. Okay. So we wanted now, the problem with this cave cam system is that anything's moving in the scene, including clouds or people, anything, it doesn't work because the stitcher can't work. And it's very hard to do high dynamic range because it takes too long to take the pictures and something changes, whether it's the shadows or whatever. So we got $3.5 million through NSF from here, and Trong's the PI of the subcontract here, Trong Nguyen, who's the head of the EC department. There's a whole gang of us working on this thing. And the goals of this are to take a full 360 by 180 at 30 frames per second video to get the acuity up to what we're used to, which is a half a gigapixel per eye, basically. In other words, as good as you can see, and to make it reproducible so that people can use it. So here's the pictures we had from the grant a couple of years ago, and these are based on a prototype I'll show you in a minute that worked. These are Raspberry Pi cameras, which you can't get anymore. And here's what it looks like in an exploded view. Now, notice that cabling becomes the key problem in a lot of these things. And also, there's a bunch of technical issues about how to get the cameras to be in stereo at your interocular distance, which you want, and also to synchronize and have global shutters and all these kinds of things that just don't fall into your lap. Lots of different concepts. This is one. Harlan Baker is a guy who works with us. He is from HP, and he's been working on this stuff for a long time. In fact, that cross-eyed thing we just showed you, he had a patent on it until HP decided they didn't want the patent anymore and just didn't want to defend it and just released it, which is great for us. And this is a different thing. This is taking advantage of the fact that depth, you need less information for depth than you need for your visual acuity. And so this camera's basically got little cameras that are taking a lot of getting a lot of depth information, and big cameras, so to speak, big cameras that are focusing on higher resolution images. This is a different thing from the stitching we're using. This is really not trying to reconstruct 3D from all of these cameras. It's a very different concept. Our test system was using these Raspberry Pis, and that's the size of the sensor. It's the kind of thing that's in your phone. We built this prototype, which actually worked. Again, notice that the cables are bigger than anything. We were able to make it work in video and in stills. And then the Raspberry Pi went away, and the SpyCam thing came out, and it turns out you can make it a lot smaller. From our tests, the critical diameter of something like this is like 6 inches. Smaller is better. 8 inches, that's another whole lecture. You can't actually resolve the stereo very well. Now, it turns out that this idea has occurred to a lot of people. So this is a quick set of people who are doing this in one way or another. And because it's an obvious thing you want to do if you're going to have all these head-mounted displays out there, you got to make images, right? And you're not going to make them all with computers, right? Because you want to see real things. And or mix real things and so on. And of course, it's so much easier to do point of camera at something than it is to actually create it from scratch. So this is an obvious idea. And of course, now that Google's into it, it's about time for us to get out. But also, so's Microsoft, and so's Facebook, of course, and so is, and the rest of the lecture is going to be talking about, for a few minutes, just about this. So people say that the cumulative worldwide sales of VR head-mounted displays will reach 200.1. I love the accuracy. Million units during the period from now through to 2020. And then there'll be 76 million units a year, 76.7 million units a year. And the the revenue will be $21.8 billion, I guess, in 2020 dollars, with a compound annual growth rate of 142%. So, if you believe this is the place to put your, your retirement savings in. Again, I don't know where they get this from, but Lots of people are jumping into it. This is the Samsung Gear and Project Beyond. Beyond is the camera. Looks surprisingly like the camera, like our Camelot, except it's, in fact, I'm sure they read the same patents. It's, but it's lower res. Now, if you're trying to match the resolution of a cell phone, it's not so hard. Not so hard. But it still looks like crap, right? So here's one that's trying to be a bigger one. And this one has a lot of cameras, but they're not shooting in stereo. They're trying to create a high-res scene. Now, if you have enough overlap, you can actually make this work. If you throw away like 60% of your pixels or 80% of your pixels, you can actually do a good job of recreating the scene. And there's a discussion of it I'm not going to go through. But they basically say doing it in stereo doesn't work. GoPro has a thing like that. A lot of people make little frames to put GoPros in. There's a company called Jaunt who has this lovely space age looking thing, which is pretty close to the same deal. And I'm not going to start going downhill. Okay, we started at the non-obtainium to expensive stuff. Nikon has a camera, which I don't know if it's for sale yet, but they certainly have, I think you can pre-order it. It's got 2 lenses on it, and there's a problem with doing really wide-angle lenses, though, because the stereo collapses at the edges. So it's, you know, in head-mounted displays, we're assuming that if you're looking at a rock concert or whatever they're trying to do, that you know, you're not really going to expect to have stereo. A lot of these things really don't do stereo anyway. Here's one that does, they claim, the Nokia $60,000 box. Now it shoots in front in stereo, and up and down it's mono, and of course obviously it doesn't shoot in back because it's got no cameras back there. Here's one that I like because it doesn't do stereo, but so you understand what the difference is. 360 is a single surround image versus stereo, which is effectively 2, 1 for each eye. Now this one cleverly solves the problem of where do you put it? You know, so when you have a camera, you know, cameras, you point a camera out, right? You've got the cameraman, camera person, frames the scene. There's all this stuff about cameras and their framing and everything else. And when you throw all that away, you know, I wrote a paper a long time ago called The Defenestration of Windows, a joke that nobody got. But because defenestration in English doesn't mean removing windows, it actually means jumping out of a window, but it's a different thing. But what do you do when you've got cameras all over the place, you know? Where do you go? Where's the camera person going to be? You know, selfie all the time? You know, yeah, that's one way to do it, and it's probably going to be the dominant thing. But, you know, you stick the thing on something or on a tripod or hang it or throw it up in the air or do something with it so we can take pictures all around without having you in it. And then, of course, you need remote control, which fortunately is trivial. So these things, you know, we're going downhill in price. Now, here's the thing called Bubble Cam that you can, some of these things you can buy, you know, and get them in 2 days with Amazon Prime. Here's the thing called We Make VR, and I haven't been able to figure out the cost of this one, but it's trying to do stereo cameras, and everybody in the field has pretty much figured out that isn't going to work like that. Okay, it's one of those things that looks like it should work, and you could probably write a grant proposal about it, but it doesn't work. So here's a little frame that somebody made for Hero 360 Hero GoPros, and you know, it's a lot of money for a frame. Of course, the next person comes along and makes it for half the price or a tenth the price. Here's another one that's doing stereo, a couple of stereo things. This one, I don't think you can actually buy. Here's one that is kind of the cutest one, and for $500. Kodak's got like half of the Nikon one for $399. And then there's the Kickstarter version one. So here's one that uses a trick that you can't do in stereo, but you can do in mono, of pointing a camera up into a parabolic 3D lens, circular parabolic lens. And, but, you know, as these people are trying to do this Kickstarter, here somebody's got one, Jürgen has one of these things for $349. And then there's the Ricoh THETA compact camera, which you can buy and exists and works. And it's the size, you know, a little thing, right? Half the size of a cell phone. And it actually does a pretty good job in mono. And then this thing, which I assume is called the fly because you throw it up in the air, but I don't know. Here's another one that was actually meant to go on your, I think originally on your dash, on the dash of your car. We're going downhill now. So here's something that fits on your iPhone and uses that same idea, but it's only $30, amazingly enough. And all the way at the bottom I could find was this accessory for the iPhone, which is the same principle, for $14. Now, how can you make something for 14 bucks that works like that? I don't know. You basically have something, the resolution is so bad that it's just a gimmick. Now, I got really excited when I saw this. So, because I was searching in Google shopping and finding things. So here's a VR 360 digital camera bag. So I think, wow, this is when they start to accessorize these things, you know, when there's a camera bag. And when I first saw it, I thought, wow, this is for you, like your Oculus Rift or something. You know, they're accessorizing. You know, next thing I have little dingles that hang off them or something. You know, like so. And then I looked carefully, and this Olympus does have a camera. It is called the VR 360, but it's a regular snapshot camera. It happens to be pink, and it's just a regular snapshot camera. They called it the VR 360 for some reason, but it didn't. It isn't. It's just a snapshot camera. But again, I got kind of excited. So my question to you, ending this up, is what are you going to be doing 40 years from now? You know, those of you who will be around then, which is more than half of this room. These are only the current grants that we have and collaborators. I've been very lucky. I was a poor faculty member using consulting funds to populate my laboratory with equipment, and I ran into Larry, and he got me addicted to money, and that was 30 years ago. Anyway, these are all the people who fund us, and if you do a presentation like this and you have an NSF award, it's actually critical that you put a slide like this in case you've never noticed. So with that, I want to stop and have a few minutes for questions, and then we'll take anybody who wants to over to the wave. So thank you. All right, who's got a question? You've got a question, Jim, I'm sure.
Just directly, Scott.
Okay.
One, I actually worked on VR stuff a little bit as an undergraduate at Brown, so it was really fun to. Your tour was really great, and one thing that you can sometimes think about creative ideas as being like stocks, and I feel like virtual reality and speech are two stocks where, for many decades now, the stock price has been higher than warranted by the short term, what happens in the short term. And yet I think there is a fundamental intuition there that makes sense. And with speech, we're actually starting to see some things change. So for, I don't know, decades now, we've been promised that speech was 3 years off. And then it actually all of a sudden started working. And I'm curious whether, I mean, it seems like certainly Silicon Valley this year has decided that VR is at that point right now. But I'm curious what you see, you know, clearly for medical applications or other buildings, VR is going to be transformative. What are some of the other domain areas where you're excited about?
That's a hard question. You know, if I knew, then I'd probably be working at Apple or Google today. That is a hard question. Well, I think where I'm putting my money, which is the chancellor's money, is into building a VR lab in the basement in the old Moxie space. And so we're putting a lot of money, a couple $100,000, into building a state-of-the-art, student-oriented, you know, student-centered VR lab that will have like 40 Oculus Rift systems and other stuff. And, you know, because the thing that we can compete best here is teaching students to do these kinds of things, right? I mean, how do you compete with the billions and billions that Oculus and Hollywood and other people are putting into content development, and you do it by doing what they can't do, which is teach people. And to get people to push the envelope, to get the artists involved, who are the ones who push the envelope in our field. I've always worked with artists as fundamentally as part of what I do. So that is an important observation. Now the other trick is getting the tools, the software and the hardware, at a level in which they're essentially throwaways. So I remember I used to tell my students that there'd be a revolution of computing when computers cost less than 3-year-old Buicks. Of course, that was a long time ago, you know. Now it's less than 3-year-old Buick toys, right? That has changed. The quality, of course, of the head-mounted displays will only get better. You know, one of the things that came and went rather briefly was the 3D TVs. And part of that is because it's really hard to shoot 3D. And actually, you know, it just changes the paradigm. Now, it works better with video, it works better with VR. It doesn't work with romance. I mean, 3D romance just doesn't matter. It's annoying, as a matter of fact, you know. So everybody always tries to make the new medium do what the old medium did, but maybe faster or a little glitzier or something. And this is really, as you say, a paradigm shift. It's a change in the way things are done. And we have to get it in the hands of students, because they're the ones who are going to do it, right? And this lab will include good audio, you know, Shirok's 3D audio stuff and so on, and make it so people can do things that we've never seen before. Now, this is what I liked always being about computer graphics, is I got to work with top scientists, as they would say, and to help them visualize things that they'd never seen before, and I'd sure never seen them before. I mean, way back when I was a graduate student, I was working with a math professor, and I programmed up something he did. And remember, everybody else was using punch cards. And I was using this wonderfully interactive system, this PDP-11. And I looked at him and said, "Is that what it's supposed to look like?" He said, "I don't know. No one's ever seen one of these before." You know, that was kind of a transformative moment. So that's really, I mean, my effort and money is going into the students here. So. Next question. Anything else? All right. Well, I know I've overloaded you when you don't have questions to ask.
I think everyone wants to see it.
Okay. All right.
That's what they're excited about.
Is that what you don't want to delay that? Okay. Fine. Let's go.